All right, I haven't looked at these problems too much, although that's not different from the usual lecture problems. I don't usually look at the usual lecture problems that much either. I'm going to show you how I approach them, show you my thought process, maybe make some mistakes. Let's see what happens. Trying to do problems that are a little different from the lecture problems here. So let's start with 114. This one wants you to really visualize and get the difference between the shell method and the washer method. Okay, so once you use both methods, I'm only going to set it up unless it's an interesting looking integral, and then use technology to graph the functions and draw a typical slice of both by hand. We've kind of been doing this in the lecture videos. Let's start with our picture. It says we can use technology, but I think it's going to be easier to do it by hand. Y equals 3x. And y equals 3. And it's the region between y equals x equals 0. All right, so it's this region. Rotated about the y-axis. All right. So I'm actually going to copy this picture twice. Wait, does it let me copy it on the same page? Yeah, there we go. Let's copy the picture twice and set it up with the shell and the disc or washer. All right, it's technically washer here. I just want the same name for both of them. Basically the same method. So here we're rotating it about the y-axis, so we're going to need things in terms of x for the shell method. Everything's already in terms of x, so we're good to go. Let's get our little picture. So it's in terms of x. We need things in terms of x. So that tells you that we're going to have these vertical rectangles in terms of x. Again, we're rotating it around like this. So we're looking at the volume of these little shells. And again, it's the full shell. I just don't usually connect it because it's harder for me to draw it that way. But I'm only drawing half the shell. Not even half the shell because I'm not drawing the bottom. But yeah, this shell. And again, if we spread the shell out, right, the radius is 2 pi. Or sorry, this distance, this circumference is 2 pi times the radius, and the radius is just the x-coordinate. What's the height of this guy? Well, it's blue minus green. Blue minus green is 3 minus 3x. So we just add up infinitely many of these, and we get the volume is 2 pi integral in terms of x here. X is going from 0. This is the point 1 comma 3, I believe. So x is going from 0 to 1 of the bottom. You can really write the 2 pi in here if you want. I think if you're going from here, including the 2 pi on the inside makes a little bit more sense. If you're using the formula, I think writing it this way makes more sense. Times the other one, 3 minus 3x, and you add up those infinitely many things. And that's what the shell looks like. Washer method. No, it is the disk method here. Gosh darn it. Dag nabbit. Is going to be sort of similar. Let's draw this out. Now we have things, we want things in terms of y. So we're going to draw rectangles from the other orientation. We draw these rectangles and we make a disk out of this. Area of a disk, pi times the radius squared. Okay, we will have to solve for x though. So, oop, that is too thick. X is 1/3 y. So now this is going to be pi times the radius squared. Is the disk method. It's in terms of y here, so y is going from 0 up to 3. And at any point, the radius is just the function value in terms of y. The x-coordinate, which is 1/3 y. We're squaring that radius. So again here, disk method maybe looks a little easier. They're both fine. Can check your answer with the textbook. Should get that these are the same values. I'll check my answer just to show off those good habits. 2 pi integral from 0 to 1 of x minus x times 3 minus 3x. dx, again, another pi. The other one is pi times integral from 0 to 3 of just 1/2 y squared dy, right? Nope, it wasn't that. 1/3 y squared. There you go. Same answer. Hooray. Next problem. 149 from the textbook. Okay. Find the volume generated when the region is rotated around the given axis. So the region is to the left of x equals sine of y, and to the right of y equals x, rotated about the y-axis. So let's try to give a picture by hand, and if it's not good, then we can pull up technology, but we should be able to. We're looking to the right of y equals x. Looks like this. Let's color code things. And to the left of x equals sine of y. So we notice sine curve looks like, right? Sine curve is going to look like this. But now it's x equals sine of y, so it's going to be kind of the twisted version of that. And we're looking at, oh, I didn't color it. Well, that's going to be white. And now there's two areas that bound here, right? There's this guy on the left and this guy on the right. It's a little ambiguous, but because it says to the left of the sine graph and the right of the other one, that tells us that indeed we're only looking at this red area here. I wish I didn't draw my graph so tiny. We want this rotated about the y-axis. So again, do you want things in terms of y or terms of x? I think the washer method's going to make more sense here. But you can use the washer method or the shell method. Let's set up both. Good practice. All right, so if we use the washer method, all right, then we want things in terms of y. And we're just going to find, and this kind of looks like the shell method, but we're doing this little washer over here. So it's going to be I times the integral in terms of y. Y is going from 0 up to, what is this point? The x coordinate is 1 here. Yeah, this 1 comma. No, this is not 1 comma 1. Wait a minute. What is this intersection? I don't think this is anything nice. When is x equal to the sine of itself? When is the sine of something equal to itself? Well, 0, 0 is the easy one. The other one is not so easy. We'll use technology for this. Y equals x and x equals sine of y. The picture does not look like I thought it did. What? This is why we do these ones. I thought this one would be weird. To the left. Oh, it's sine of pi y. Oh, that makes things easier. All right. sine of pi times y. So why does that make it easier? So normally the period of sine is 2 pi. But now that's getting compressed. Now the period is just 2. So we know this guy up here is 2, this guy is 1. We know this is at 1/2. And we're still going to use, we could figure this out. Let's graph it. Okay, see, add the, so where does that intersect? At whatever coordinate that is. I wonder if that is something, I don't think that's anything in terms of pi. But maybe it is? Is that pi over 4? No, it's close to pi over 4, but it's not pi over 4. Well, the problem did tell us to use technology, right? No, it didn't. Oh, well, you can use technology for this one. I don't think you have to, but we're going to. So this is the point. 0.736. Great, and if you set up the washer method, it's going to be in terms of y, so it's going to be the right curve, which is going to be sine of pi y squared, minus the left curve, which is just y squared. If y equals x, then x equals y. And y is going from 0 up to 0.736. If you use the shell method, you have something. Now we're looking at this shell, which is blue minus white. So it's going to be 2 pi. Now we're doing it in terms of x, which is also going, x is doing the same things. But now it's blue minus white in terms of x. Blue is just x minus white in terms of x. Well, we're going to have to solve that. X is sine of pi y. That means arc sine of x equals pi y. The y is 1 over pi, arc sine. Ooh. Okay. And then this is multiplied by x. I almost forgot my x from the formula. So the second one, you do integration by parts on, probably. This is a bad integral. This is not a fun integral to do. So here, you're going to want to use the washer method on this one. Now, when you check your answer on this one, you get something very unique, something I did not expect at all. And it's because my picture is not quite right. The actual, so I have mine like intersecting kind of here, but really what the line should look like is the line should intersect higher on. Now, what do we know about arc sine? Because I'm saying this is true, but it's not. Arc sine only looks like this. The range of arc sine is just from negative pi over 2 to pi over 2. So this doesn't even make sense. Take arc sine up to 0.736, which I didn't realize that 0.736 is bigger than, yeah, so this is going from negative 1/2 to 1/2. And we need to go a little further. So that's actually why this integral doesn't really make sense at all. If we really wanted to use the shell method, we'd have to get a second piece for this red section, which we could do. We could do it. It'd be a bit of a pain. Don't use the shell method here. Use the washer method here. All right. That was cool. I was not expecting that. I like having these examples where I show you guys, hey, make sure that your region of integration makes sense with your function. But this one slipped past me, actually. Nice. I'm happy to see that. Happy to experience that. Cool little thing right there. Oh, and you can see it visually on Desmos. I don't think I showed it on Desmos. This is what arcsine looks like. Or this is what the y equals 1 over pi arcsine looks like in white. And you can see, yeah, it doesn't go high enough. Because arcsine is a function. And a function has to pass the vertical line test. So that's why arcsine stops here, to keep it a function. Nice. I shouldn't get so excited about this, but I am. Okay, next problem. Actually, I should get excited about that. It's my job. 159. All right, use the method of shells to approximate the volumes of some common objects. So very similar to what we did at the start of 2.2, but can we do this with shells? I haven't done this in a really long time, so we're going to see how this one goes. Again, like part of the goal is to kind of show you my problem solving process. So first off, looking at 159, it's a cone. And if I want to model this with a picture, it's probably going to be easier to... No, I think having it this oriented, sometimes it's easier to flip things upside down. Let's just start with what we have though. So if we want a cone, right, that's going to be this line rotated about the y-axis. So what is that line, in other words? Well, if this is going to be r, this is the radius of the cone, is this distance r, then this has to be the point r, comma something. Let's have r, again, this will be our x-axis, this is our y-axis. We're rotating this like so. So then the question is, what is the y-coordinate here? It's going to be the height. And what is the height? We know it. We can express it in terms of... Actually, no, we can't express it in terms of r. There's going to be some value h. So then what's the equation of the line? Well, it has a y-intercept of 0. And what is its slope? Slope is rise over run. Slope is h over r, right? Because we go up h over r. That was a little hard to see. We go up h over r. That's our slope. So we know the equation of this line is y equals the slope times the x-coordinate. Now, do we want things in terms of x or terms of y if we're using the shell method? Well, we want things in terms of x because we're rotating about the y-axis. This is what we like. Now we're using shells. Do we want things in terms of x? We're going to have these little guys. These are our little shells. The radius is just x. We need the diameter, 2 pi x. And the height is just going to be a height of h minus this height, which is h over rx. And that lets us set it up. Volume is going to be, maybe we'll do this one out all the way. 2 pi integrating over x. X is going from 0 up to r. Of the x-coordinate times the y distance, which is the line y equals h, right? That's this top line up here. Y equals h minus the bottom line, which is h over r times x. And now we can integrate this. H and r are constants. X is our only variable here. Let's be a little careful. Let's FOIL this out. We're going to get x times h. Since h is our constant, I'm going to write h in front. Minus h over r times x squared. Now we can take the antiderivative. Also, we know what our answer should be, right? Our answer should be 1/3 pi r squared h, I think. The antiderivative here is just going to be h over 2 times x squared minus h over 3r x cubed, evaluated from 0 to r. Now we very carefully evaluate and don't make silly Jason mistakes. You plug in r, you're going to get h over 2 r squared minus h over 3r r cubed. Plug in 0, get 0 minus 0. I'm nervous. Oh, I'm not. I was nervous. It's okay though, because the r's cancel. Woo! Right, one of these r's is going to cancel with that r. So this is 2 pi times just h over 2 r squared minus h over 3 r squared. Well, a half minus a third is a 6, so that's h over 6. So what's 2 pi times h over 6r squared? Well, we get some cancellation. The number is 1/3. We have a pi. We have an r squared. We've got an h. Whoa, I did it. Not that I want to sound surprised about that. But I've been making a lot of silly mistakes in my definite integrals recently. There we go. And that's how you do this sort of thing. I think it's easier with the shell method than it was actually with our cross-sectional areas, the beginning of 2.2, before we introduced the disk method. I think that was actually harder than this. Who knows? And 163 is a really fun one. Well, really fun looking one. We'll see how good it actually is. Consider He region enclosed by the graphs of some function f of x, some function 1 plus f of x, x equals 0 and y equals 0. And x equals a, where a is bigger than 0. What is the volume of the solid generated when this region is rotated about the y-axis? Assume that the function is defined. We're going to assume it's positive too. So let's just draw a little picture. Obviously, we don't know what any of this looks like. Let's draw a picture. So we have some kind of function. Okay. We have some kind of function of x. And we're going from 0 up to some a. We don't know where a is. And we're looking at the region between f and f plus 1. Well, f plus 1 is just going to be the exact same shape, just moved up 1. So we have this region revolves about the y-axis. So shell method is going to be much easier here. Shell method says, well, what's the, ooh, I went too far, sorry. Shell method says, okay, we're revolving around the y-axis. We need things in terms of x. Let's draw our little x's. Our rectangles in terms of x look like this. So the volume is going to be 2 pi. X is going from 0 up to a of, well, we have a radius of 2 pi x, or a radius of x, so the diameter of that, you know, that shell like this will be 2 pi x, times the height of this rectangle, which is just blue minus red. The height's 1. Blue minus red is just 1. Any time the distance between these two curves is always just 1. So this is just going to be 2 pi. Antiderivative of x is 1/2 x squared from 0 to a. The 2 pi and the 1/2 cancel, actually. We just get pi times a squared minus 0 squared. Just pi a squared. Units cubed. No matter what the function is, no matter what a is, don't believe me? Let's visualize it. So the problem's done, the video's done. But if you want to have some fun, stick around. Let's look at this. I think there's some cool things that we can graph. All right, so first off, we're looking at the area for this volume. We think the volume should be pi times a squared. We'll need a slider for different values of a. And we're looking at, we're going to need an x too. Have the integral from 0 up to a, 2 pi times x times, again, this is f of x plus 1 minus f of x. And then f, well, let's just choose one. What does this look like for x squared? So first off, notice that these integrals match. We also want to, and let's say, again, let's specify a domain restriction. So we have to calculate the integral. The volume is going to be the same. So these top numbers should be the same. And as a gets bigger or a gets smaller, we have the volume for any of these a's. And we could change these functions. What if f of x was just sine of x instead? Well, different function, still the same volume. And we can change our value of a to get a longer solid. And you can put any function you want here, then it should work. Turns out it doesn't even have to be a positive function. It's still true. I remember for these requirements, for these theorems, these rules, we assume positivity, or we assume non-negativity, but that's just to make it a little easier to calculate. You can always split things. In fact, I don't know if there's almost no theorem that I can think of where positivity is a requirement, because most functions you can just split up into piecewise functions as a positive component and a negative component and do things individually with each component. But that's a much more complicated topic than calculus. So again, you should be able to choose any kind of function that you can think of here. I'm apparently not very exciting. I can't think of a lot of good ones. I don't know, we could do like x times, x minus 1 times, x plus 2 or something like this. And then do it that way. I don't know. It all matches. That's what we're doing. Shortest selected homework problems video ever. Let me know if you have more questions on these ones. And enjoy the shell method. I hope you love the shell method half as much as I do. Or maybe more. Bye-bye.